In this video, we will consider Euler's derivation of the rigid body equations in the stationary reference frame. We will follow Euler and consider an infinitesimal part of the rigid body to obtain Euler equations for rigid body rotations in a stationary reference frame. Let us start with the definition of the rigid body given by Euler. A body is called solid, or in modern terms rigid, whose interior is not subject to any change, or which is such that all its parts constantly maintain the same relative position, whatever motion the whole body may have. Now let us consider a rigid body. In this video we see what happens if one applies a small instant force to a rigid body. In general, there can be both translational and rotational motion when a force is applied to a rigid body. This rigid body also makes some translational motion, but we will consider only rotational motion and ignore translational motion, like Euler. In this case, the rigid body is a stone and the direction of the applied force is off-center, which results in a rotation that ceases under the friction. Now, let us try to understand the basics of this situation. We can say that the applied force acts in this direction. To study the motion, we need a reference frame, which we will choose as the stationary reference frame, whose origin is at the rigid body's center of mass. In this case, we have used a primed representation for the coordinate axis for future reasons. For a while, let us not consider the applied force and try to understand the situation by considering rotations. Now let us consider an angular velocity omega and an infinitesimal volume on the rigid body. The position of the infinitesimal volume can be represented by this r vector, and it can be written in this way, where x prime, y prime and z prime represents generic distances, and x prime hat, y prime hat and z prime hat represent directions along the axis of the reference frame. Similarly, the angular velocity omega can be written in this way. Then we can find the linear velocity of the infinitesimal volume by taking the cross product of omega with r. Here we should note that during the time when Euler did these derivations, the cross product was not defined yet. In fact, Lagrange defined the cross product a few years after the Euler's derivation. As it is clear, Euler didn't use the cross product, but we will use it in some parts. After taking this cross product, one can obtain the linear velocity of the infinitesimal volume in this way. Then we can write the components of the linear velocity like this. By taking the time derivative of this equation, we can obtain the components of the infinitesimal volume's acceleration. There will be terms including the time derivative of x prime, y prime or z prime. And for these terms, we can use these equations and write them without these time derivatives. And there will be some terms including the time derivative of angular velocity, which we will leave as they are. Then we obtain these equations for linear accelerations. If we multiply the acceleration with the mass of the infinitesimal volume ρ, we obtain the force on the infinitesimal volume. While obtaining this force, we have used Newton's second law. The force is equal to the mass times acceleration. We should note that this force is different from the externally applied force. This force originates from the external force, but it is the result of the atomic interactions that hold the rigid body as rigid. And it is possible to say that with the help of these atomic forces, the rigid body rotates as a whole. These three equations are relations between the distance of the infinitesimal volume from the rotation axis, angular velocity, and the force. We should note that there isn't any constraint on the angular velocity omega. It can be anything, and it can be said that these equations give the force affecting the infinitesimal volume that is necessary to maintain that angular velocity. We can write the force affecting the infinitesimal volume in this form, whose components are given in the previous slide. Now let us consider the rotation of the infinitesimal volume, which takes place under the effect of the mentioned force. The mentioned force can result in rotations around all axes. Firstly, let us consider the rotation around the x' axis. If x' doesn't result in any rotation around x' axis, then we can ignore it for the rotation around x' axis. Fy' and Fz' affecting the infinitesimal volume can be shown in this way. And let us recall the r vector representing the position of the infinitesimal volume. If we consider the right-hand rule, then we can say that Fz' contributes positively to the rotation, the counterclockwise direction, and Fy' contributes negatively clockwise direction. Since the time of Archimedes, we know that moment of force or torque depends on the distance from the rotation axis as well as perpendicular force. Then, by using the force on the infinitesimal volume, we can write the x' component of the moment of force as nx' is equal to y' times fz' minus z' times fy'. And similarly, y' and z' components can be written in this way. Then, by using the explicit form of the force, we can write the components of moment of force that should act on the infinitesimal volume. As it can be seen from these three equations, torque should be equal to a complicated function depending on time derivatives of different components of angular velocity, different components of the angular velocity itself, and different components of the distances. These relations should be satisfied for the infinitesimal volume with the considered angular velocity, and this should be valid for each infinitesimal volume, and one can say that the moments of force are distributed over each infinitesimal volume of the rigid body to satisfy the rotation of each part of the rigid body with the same angular velocity. And these equations should be held at every instant of the time. We have obtained the relation for the infinitesimal volume. Now we should obtain a similar relation for the whole rigid body under the effect of an external force. As it is clear from the situation, if we integrate the result for the infinitesimal volume over the volume of the rigid body, we can obtain the necessary relation. These are the equations that we have obtained previously for the infinitesimal volume. From the integration of moments of force on the infinitesimal volumes, we obtain the moment of force for the whole rigid body. And they should be the same as the result of the known relation of torque that is equal to R cross F. The explanation is simple. Some parts of torque on the different infinitesimal volumes should cancel each other, and the result should depend on the external effect only. Now we need to integrate the terms on the right-hand side. There are two different types of the terms. One term includes the integration of squares of different components of the radius vector, and the other one includes the integration of multiplication of different components of the radius vector. As it is clear, since they depend on the distances and properties of the rigid body, they will give different results for the different rigid bodies and different rotation axes. We can define mentioned integrals in these ways. Three of them seen on the left are known as moments of inertia, and 6 of them on the right are inertia products. It is clear that there is a symmetry for inertia products, Since one can change this x prime and y prime, and the results of this integration does not change, and it is similar to the other integrals. Finally, we can write the equations describing the rotation of a rigid body in a stationary reference frame in this form. These equations describe the rotation of a rigid body under a torque in the stationary reference frame. There are some further points that should be considered in these equations, like the dependence of moments of inertia and inertia products on rotation, or equivalently time. This rotation or time dependence results in intricate relations. Euler found ingenious solutions to these, which we will consider later. You can find the references in the explanations of the video. Thanks for watching.